Okay. So let's have a quick revision as what we have gone through in the last session. So in the last session, we have gone through the various aspects of processor architecture, and there we have seen an example of Core i7. And in Core i7, we have gone through the performance core, efficiency core, as what exactly we mean by performance and efficiency core. What is the major changes that has been brought into the modern architecture? There is a concept of turbo frequency, and using DVFS, that is dynamic voltage frequency, the voltage of the processor is being varied uh, dynamically based on the need, based on the temperature parameters, and accordingly the speed is varied just for having the optimum performance along with the cost effectiveness. Because if only Microsoft Word is running and your capacity, processor capacity is of 5.2 gigahertz, so there remains no reason for running the processor at 5.2 gigahertz when the Microsoft Word or the capacity that is exactly required may be maximum 2 gigahertz, right? So ultimately, it's the input also that will make the difference, not only the processor speed. So if the input to be processed is coming at a slower speed, so what you will be achieving, even if you are having a processor with a greater speed. So uh, the main idea here is mainly for the data centers or so. For an individual user, it may not impact much. If you see the base power is 55 watt. If you see the turbo power, then it is 157 watt. Okay. And minimum assured power is 45 watt. So what you can derive out of it is your power will vary from 45 watt to 157 watt, right? So altogether, even uh, if the processor runs at the full speed, in that case as well, it will not be more than thrice, right? And in terms of our home electricity, it doesn't impact much, even if it is running at a maximum speed. But when it comes to data centers, and when data centers are having thousands of processors, so this multiplier is huge, right? And for these purpose, ultimately the optimization is being done by the processor manufacturers, right? So later on, we have gone through several other parameters. You can definitely refer all these parameters. Then we have seen what about the logical cores. Again, coming to the concept of performance and efficiency cores. We have gone through the calculation, the basic formula about the performance and efficiency course. Then base frequency logic, turbo boost, why base frequency is increased, what are the favorable factors that increases the base frequency, right? And how it is being managed on a variable node, how frequency varies. So we have seen that ultimately voltage is being varied, and because of that, frequency is varied. Okay, so we have seen the concept of threads, we have seen the concept of handles, where handles correspond to reference of a system resource. Okay, and later on, we have gone through one good law known as Amdahl's law that gives me the potential speed up when we are using parallel processing, right? So recently we came across one of such situation. So the GPU cluster that we are having, So that GPU cluster is having GPUs that is NVIDIA H100 NVL, and each GPU is of 94 GB, right? So we usually create virtual machines, and when we create virtual machines, uh, whatever be the required quota as by the startups that we onboard, right? So supposedly we have given one startup 4 slices. So what exactly happens is NVIDIA allows to slice the GPU and allocate as a separate workspace. So this 94 GB can be sliced into maximum 7 slices. Okay. So 7 slices, it will go somewhat around 13 point something GB per slice, right? So what exactly? Suppose I have given some user 4 slices. So altogether, it will come up to the capacity of 52 GB, right? But when they were trying to draw the maximum capacity of this GPU, so ultimately they were not able to draw it because of the slicing. Okay. So what I mean to say is, then I suggested that if you program in such a way that you can have full parallel code running on 4 GPUs, and somehow at a later stage, if you can merge the result, right? So that way you can make maximum use of your GPU. So few of them have adopted it, and few of them said that no, ultimately we will be requiring a combined one because we cannot make it a parallel program. So later on we merged it, right? So ultimately when we are having multiple cores, so that way if your program is capable enough of running on multiple cores, then what exactly is the speed up you may witness. Okay, so for this we have seen this formula, right? And apart from this, we have, so this was the formula corresponding to a speed up when we are having n parallel processes, and f is the fraction that is being parallelized. So if this is the fraction, and whatever remains is 1 minus f. So this formula we have seen, and one practical problem we also have gone through. These are some of the derivations that you can have when f is small. It is not putting any impact even when we increase the number of processes to 1,000, right? So you can have a look. Even if you increase it to 1,000, then also there will not be much of the impact, because from 1 it has reached only to 2, right? Means only double the speed, but even if you increase it further, it is not putting much of the impact. And see the impact once it is the value of f is near to 1. Okay. One more derivation that you can have out of it is, after a specific number of processes, whatever be the hike you will be doing in number of processes, it will not have any kind of impact. It will go more or less on a constant note, right? So this is what we can derive it. And later on, we have gone through the concept of MIPS, that, okay, what exactly is uh, MIPS, that is millions of instruction per second. And this we have done mainly to assess the performance, because performance may not only be assessed by the capacity of the processor, because I need to make into consideration the instruction set as well. So whatever be the instruction set, what is the number of cycles I'll be needing corresponding to executing any instruction. So all these things we have considered and finally landed to the thing that is, if I have to get the MIPS rate, then corresponding to the program that is being written, or in general, if I consider all the instruction, then I have to calculate the cycles per instruction in the sense average cycles per instruction, or we can say average cycles, or we can say cycles per instruction to be very precise. And here we are having the frequency. So that way we can have a good comparison. Later on, we have gone through few of the case studies in terms of clusters, in terms of processor, RAM. So you might have gone through this. Okay. Next, we have started with cache memory as what exactly is cache memory and where we can utilize it. So we had just started and gone through the various aspect as what is access time, memory time. This is in general corresponding to the memory, and we have seen a comparison with reference to the speed. So this is where we have left. Okay, so you can just have a look. So this is the general system corresponding to which we have taken the snapshot, and you can see the difference in speed with reference to the various caches. Okay, so we'll just enable the mic as well. Mic. Okay. So you can just have a look. Uh, see the speed difference. If the main memory is of 32 GB and the speed it is having is 19.2 Gbps, and see the difference with L3 cache. Even if we compare it with L3 cache, then also it is almost 2.2 times that of main memory. And if you keep on comparing it with L2, then almost it is 7 times of L2 cache, right? And L1 you can means it's way beyond. L1 cache, it is 646.3 Gbps. So there was one memory test application. We have executed that application. If you see, then this was the application we have executed, Passmark Mem Test 86. So that usually do various tests and calculates the speed, right? So it's a huge difference, and that's why we have seen in the last session that because the difference is huge among the and this is about the memory only. So we are not at all comparing the processor speed. So it's in gigahertz generating clocks at 10 to the power 9 magnitude, right? So it's huge, right? So in order to bridge the gap that the processor and your main memory is having, we are having the concepts of cache, that is L1, L2, L3. Cache is there. Okay. So this is the Xeon system, the cluster I was talking about recently, where we are having the GPUs within those cluster GPU nodes are there. Okay. So see the difference. So earlier it was something, so memory is 1.9 TB and the speed is this 13.8 Gbps. Okay, and here L1 cache it is 299.2 6 Gbps, right? And it is Intel Xeon Gold 6548Y plus processor, right? So now coming to the addressing, we will first see the basics of caching, and later on we will see how it is being utilized in cloud computing. The core concept means once we establish the foundation, after that at least we will be able to go through uh, the core concept of caching, right? So just have a look. So these are the common conventions that you will be having, and somewhat numerical is always preferable through the concept of caching. Okay, so you can see that when we are naming cache, so one unit is called as block. Okay, and these we are calling it as lines, right? So these are lines, and if you have gone through the virtual memory in operating system, so you just have to map it with the same concept. So corresponding to the virtual memory in operating system, what we were having is this is our RAM and this is our HDD. So this is just the analogy I am giving. But here in terms of cache, we will be having this is our cache, this is our main memory. The idea here is the processor when generating the address, okay, so we'll be generating a common address, and through that common address ultimately it will search in the cache and see if the word is being found here in the cache. If not, then a reference is made to the memory, right? And ultimately being that word is being brought into the cache as per the algorithm uh, being followed, right? So it is being brought into the cache and later on accessed by the processor. And any subsequent access will then be done through the cache only. Now, your question may be about the size. Okay. Why? Because the size of cache and size of your main memory will vary considerably, right? If you see the difference, then it is 60 MB. So even if I compare it with L3 cache, right now we are not considering L1 and L2. We will see what happens with L1 and L2. So even if I do this comparison, then it is 60 MB, and my main memory that I have taken in this process, in this particular configuration is 1.9 TB, right? So it's huge, right? So we leave it over here. Even if we go this way, then also it is 33 MB for cache, and here it is 32 GB for main memory, right? So first we will go through the concept and then we will see how exactly this mapping is being carried out. I hope you got the concept. Whatever be the blocks, so if you see, then these blocks, block is one terminology that we are utilizing over here. So the block length over here, that is the keywords, will remain same over here as well. Rest, whatever be the number of bits remaining, we'll see some numericals. That way, things will be more clear. So whatever be the number of bits remaining, so those bits will be taken as tag, right? So that the mm, width of the address can be maintained. We will see further. So this is the basic read operation that I have already explained. We will see in terms of a flow chart. Okay, so read address. So RA corresponding to read address. Okay. So receive address, read address from CPU. So processor generates an address. That address is being picked, and then we check that block, whether the block is containing the read address in the cache. If so, then it will fetch, and the process gets completed, right? If not, then it will access the main memory for block containing the read address, right? What I told you. If not found over here, so it accesses the block in the main memory, allocates cache line for main memory block. So even at the first time when it will read, but ultimately it will pick that and allocates some memory block over here in the cache, and it will transfer it to that particular block. For this again algorithm will be used. Okay. And once transfer is being made, once the cache block or cache line specifically, cache line is being allocated, two parallel activities will happen. One is load main memory block into the cache line at the same time, because it has already been read. So it will deliver the word to the CPU, and this way the process will complete, right? So I hope you have got an idea as how exactly it is being fetched from the cache memory, right? So whenever we talk about processor cache, so these will be the core elements. Okay. So first thing, whenever we talk about address, two addresses will be referred, or we can have two variations within the address. One is the logical address, and other one is the physical address, right? So we will see the difference between logical address and physical address. Okay. Then we will talk about the cache size, as what exactly is the size of cache and how it is being divided it into blocks. So there is cache, and you can see that uh, it is divided it into line numbers, and few blocks are there. Okay. Mapping function. Uh, okay, where in this diagram we will be needing mapping. Can anyone unmute, or can anyone put it on chat as where exactly we will be needing mapping? Is anyone, Ajit and other candidates, those who are usually active? Yes. In this
Uh,
whole scenario where we are needing the mapping, yes.
Mapping of
Mapping mean,
Yeah, Ravi.
yeah, please
go
go ahead.
ahead. What I am saying, mapping means like mapping of the address of block of cache memory to map with memory address.
Yes, very good. Ravi, what's your point?
Yes, it's same. Whatever cache address we have, that they're mapping inside the main memory. So the blocks which you explained, right? They must be, because they are coming from the main memory ideally, very first time. So there must be address mapped from cache to the main memory.
Yeah. So both of them are correct. So ultimately, mapping in the sense that there should be some technique, or there should be some algorithm that will be deciding, as if I am bringing some memory block say it be if this particular memory block is to be transferred over here. So it should not be the way that okay, whatever is available, we will be transferring it over there because the constraint that we have is we are addressing both of the memory through the same address. Just try to understand the difference. If it would be that, okay, I'm able to locate it anyhow within the cache, then I could have put it in any of the available space or I could have replaced any of the block within the cache. But the thing is, we are generating a common address and that address itself is being utilized for accessing cache as well as your main memory. So that way there will be a bit of restriction in a specific area where a particular block can be placed. So if this three block needs to be placed, then based on the algorithm, I should be putting it into a specific line number so that it can be fetched at a later stage. Okay, so we will see that there will be mapping approaches. One is the direct mapping, where we will be having a direct map. Say it be if I can calculate the modulus. So based on the modulus, I'll be able to get it. Say it be if the line number is 20, sorry, if the number memory block is 21, and if altogether four blocks are there, and if I do the modulus, so ultimately one will come. So that way, in the first line number, I can place it. We will see the practical example. Associative is one more mapping. What happens with direct? So whatever be the disadvantages of direct, we are overcoming those disadvantages in the associative mapping, where a complete area will be available or we will be free to store it in any of the block, right? So these are the two extreme. Here it will be specific. Here in associative, it will be somewhat generic. What I was telling you that okay, can we place it in any of the line number? Set associative is the mid solution of both of them. That is, taking advantage of both of them, you can decide that what exactly will be the algorithm in the sense that taking advantage of direct as well as associative. Okay, replacement. We need to replace the pages within cache because say it be if the whole cache is full, somewhere all valid pages are there within the cache, the blocks are full, and ultimately there is some new memory address generated by the processor which is to be brought into the cache, then which line number to be replaced, right? So deciding on this will be helped by these replacement algorithms, and many of them are clear by their verbal meaning itself. One is least recently used, first in, first out, and least frequently used. Okay, right policy. Uh, Again, you may be having a question that we may we are using two versions of the same data. Why? Because uh, that data is being available into the cache as well, and the same data is available in the main memory as well. Okay, so whenever some changes are being made, so supposedly processor does some processing and some changes are being made at the cache level or the data that is present in cache. So what is the strategy you will be following to update its version that is there in the main memory? So that particular methodology will be having two variations. One is write through, other one is write back. Okay. So size can vary, but what exactly will be the line size? So the line numbers and all, making a decision on this will be the line size we will see, and number of cache. So single, two level, unified or split. So right now we can see that nowadays we are using three levels of cache. So how things are being handled when we are having three levels of cache, right? So cache, I think we are clear about what exactly is the cache. There is a huge difference between the processor speed and the mean memory speed. And just to bridge this particular gap, we are having the memory hierarchy, and we are introducing cache memory for faster access of data. So whatever be the data which is being frequently utilized, or there is probability that this data will be utilized subsequently. So that way the algorithm keeps on working by having the data within the cache, so that the speed difference can be bridged. So contains. So when do we put something in the cache, right? Ultimately, when exactly we'll be putting something in the cache? So when it is used for the first time. So we have already seen by this diagram, as soon as some address is being generated, it first search in the cache. If available, then okay. If not, then it will refer a memory, and it is being brought into the cache. When do we overwrite something in the cache? Once the cache is full and we are running out of the space, definitely we will be doing the we will be overriding it, right? So we will see a basic design, and then we'll be moving up to rest of the thing. Okay. So just have a look. So caches divided into blocks, which may be of various sizes. The number of blocks is usually power of 2. That's quite obvious. Okay. And right now we will defer utilizing the difference between byte and bit, right? So at a later stage we will encounter it. So just have a look over here. So if it is 8-bit data, okay, and say it be, if you are having overall 4, 5, 6, 7, 8, right? So altogether it is 8 blocks. Okay, so data is also 8-bit and 8 blocks are there, right? So ultimately for addressing 8, I'll be needing 3 bits, and the data itself, which is of 8-bit, right? So this is the basic structure. Now there are several questions that should be answered whenever we are doing the arithmetic or the mathematics corresponding to the cache memory. Okay. So most of this are already answered, but at least you should brainstorm as what exactly are the points with reference to cache. Okay, when we copy a block data from memory to cache, where exactly we should put it, right? So this will be referred by your mapping, or to be very specific, because it is being replacement. So yeah, it's mapping, but whenever it comes to replacement, if the block is full, then at a later stage, we will be needing the replacement algorithm as well. What exactly is the methodology we will be using to declare that the data is in cache or not? Okay, we have seen this diagram, and I told you it's been very hodgepodge, but if you are connected right from beginning, I think you will be able to get it. So what we did for the first time is receive address from this, and we are doing this activity that whether the data you are seeking or whether the block you are seeking, whether it is in cache or not. Okay, so that way we will see what exactly is the methodology based on which we are making a decision. Okay, and the small memory may fill it. This is the exact replacement algorithm. Okay, and write operations, that is the two methodologies we have seen over here. Since we are maintaining two versions, one is in cache and other one is in main memory. So how exactly things are being carried out? Okay, so let's try to understand this with a simple example. Right, so this is you are directly mapped. Okay, mapping. I hope you remember that whenever we are mapping the memory addresses with that of cache address, when we'll be bringing any particular block into the cache. So how exactly to pick or which particular block to be picked within the cache? So based on the size, you might have understood that this is your main memory and this is your cache. So we are taking example by these small numbers so that at least the concept can be established. So right now we are looking at the concept of directly mapped. Okay, and by the color itself, you will be able to decode as what exactly is happening. So you may see that whatever be the memory address, if I do the modulus, right, say it be 14, and overall I am having 4 lines, right? So within the cache, I am having 4 lines. So corresponding to this, 14 modulus, sorry, 4. So it will go to 2, right? So ultimately, whenever this block is to be brought into the cache, so it will always be the block 2 within the cache. Right here, it is very less in number because only 4 blocks are there. So every time the replacement will happen, right? So this way you can just have the logic that
So can you
whenever,
please explain this again?
yeah, Ravi. So if you see the numbers, memory numbers, uh, pick any other number, say it be. Because what happened is ultimately I have to put it over here. Means whatever be the my cache blocks are there, number of blocks, sorry, number of lines within the cache. So correspondingly, we have to put it the memory address. So if I randomly pick 9, okay, and here I know that 0, 1, 2, and 3. These are the indexes. So if I do the modulus, so modulus is, I hope you all know that whatever remaining, only that will come out of modulus. So if I divide 9 by 4, so 4 2s are 8. So this modulus operation gives me 1 because 8 is already done and whatever remains, right? So this is the traditional method that we usually do. So if I'm writing 9, so if I'm writing 4, so 4 to 8. So if I subtract it, so this ultimately is the result of modulus operator. So it is 1. So this means whenever 9 is to be put into the cache, so it will be brought into this particular index, that is at index 1 you will be putting it. On the same way, suppose 8 is there, so 8 modulus 4, it will be 0 because nothing will remain. 8 minus 8 will be 0. So it will be put into the 0th index or the 0th line number,
So ideally,
right?
any word which is not in cache, and that needs to be brought into the cache.
Yeah.
So that its index in the main memory needs to be checked, then accordingly, based on this calculation, modular calculation, it need to be brought into the same index into the cache memory, right?
Yeah. This is the
Oh,
case with direct mapped.
direct map. But in
Yeah.
case, let's say, taking example of 9, it is
Hmm.
replacing the 1 into the cache,
Yeah. Yeah.
the blue dot. So what
Yeah.
happened to this data which is in cache?
So that is whichever is already in cache is overwritten. Means at a
Over.
later stage, if it is to be referred, then again it has to be brought into the cache.
Right.
This will not be the case ideally that every time it is being replaced. So here you may be having an impression that whenever some block is being referred in memory, and if it is not present in the cache, then always it will be replaced. But this is just to make you understand the thing.
Hmm.
At a later stage, you will find that not all the time it will
Because
be a
every
cache
time
miss.
it this is
Yeah.
being replaced, then it will have impact on
It would,
LOR, right?
yeah, obviously, correct, very correct, that it will not at all make any sense, and ultimately we will be losing all the speed just to swap the memory contained from memory to the cache. But
But sir,
definitely,
I have further question. Sorry.
yeah, yeah,
Uh,
sure, sure, come on.
but so looking at the size of the cache, it's very limited, right? Like it's a smaller than the main memory. Now
Yeah,
there there are frequent operations happening, on calculation happening, and in CAC the data, it's not possible every data will be available into the cache, and it can be retained continuously into the cache also. So
correct.
ultimately, somewhere there will be uh, that hit ratio will, I mean, miss ratio will increase, right?
That's the power of the algorithm.
Mm,
So the mapping algorithm that is being utilized, and that's the one of the reason why systems are not hanging nowadays. So
mm,
in earlier time when we were having Windows XP till Windows XP, this was the major issue
mm,
because that algorithm is not efficient, and because of that, whenever the hit ratio, miss ratio increases, so that time ultimately the system gets hanged, right? But now if you see because of the introduction of L3 cache, so if you see definitely it's not considerable, but still it's an MB, right?
mm.
So that way until and unless say it be if you are doing some kind of buffering and all, so that is totally different aspect in terms of videos or so. But on the other side, for rest of the things, 33 MB L3 cache will serve the purpose in most of the cases for the basic operations that you're doing day to day,
Mm.
right?
In case of, I want to take one example, like
Yeah.
HANA database, SAP
Uh,
HANA database. So HANA
SAP
database is
HANA,
an,
yeah,
yes, HANA database is the, it required lots of memory, and it's in memory processing capability. I mean, it has in memory processing capability. In that case, like it requires 1 terabyte or 2 terabyte of primary memory and all. And in that, in a workload like this, do we need to, while procuring the hardware or looking the hardware, do we also need to consider that cache sizing as well, right?
yeah, obviously means ultimately the data, the means why we are having this question is we are thinking from the speed of human mind,
Mm,
the way we are thinking, but just consider the speed where it is 10 to the power 9 gigahertz.
mm,
So corresponding to every clock, there is some activity going on. So this replacement and everything goes so much in a faster way. So just try to imagine the whole thing that if within a second, if you are generating 10 to the power 9 clock for a 1 gigahertz processor, right? So that way, just imagine what difference we can have when we are having 3 or 4 gigahertz processor, right? So that way, just imagine how fast all these operations would be, the switching and everything, right? But the only thing is we need to match up the speed. Rest, definitely what you are saying is correct, that in case of HANA database, ultimately the replacements will be huge. But the only thing is we have to make a difference with reference to direct access. Or
Okay.
what I mean to say is, supposedly I am using processor and I am using main memory directly.
Mhm.
So can we make a difference? Can we save the overall execution time with reference to this? So ultimately, even when my cache miss increases, until and unless it is the time taken is less than this particular interaction,
Mm.
so till that time we are in a win-win situation. So that is the ultimate motto, because anytime when you will be accessing it through main memory, we will be having that calculation as well. When we are having a cache miss, so what exactly is the time that is being considered, and whether it counters with the direct access time or not.
I am just thinking from the perspective of like we are just studying about the replacement and of this referencing part, right? So,
Yeah.
in case of HANA database, because it's process everything in the memory itself. So, what primarily the all data, most of the database sits into the its primary memory. Now, whatever processing they need to do, it will
Mm-hmm.
the particular section of the data is moved into the cache, right?
Yeah.
So right, and then so that section, whatever transaction they do, generally it's not about like in very small kbs and all. It will be in huge size. So from that perspective, I'm thinking that in that case,
Okay. Okay.
every
Okay. I
time the
got
L1,
your
L2,
point.
L3 caches, the replacement will happen. Then there will be this cache miss ratio will be high in those particular scenario, because those size of the data of the transaction is quite huge.
Ravi,
Got your point.
Ravi, this is the scenario when locality of reference comes into picture
Hmm. No,
to
that's
increase.
what the LOR. That's what I'm saying, because replacement will keep happening, because not every data will sit into the cache. So in
Yeah,
that
Yeah.
case, it
and what Ravi is mentioning is, supposedly we are having L3 of 33 MB, and my data itself that we are currently referring goes with 60 MB. So, what exactly will happen in that case? Is it what you're
yes, yes,
asking?
yes, because the data transactional data is huge. Okay,
Yeah,
so
so
in that case,
yeah,
and but the my cache size is less, right? So in that case, every time the data will be replaced. So in if the data will be replaced, that means we will have impact on LOR, which will increase the miss ratio. Right?
yeah, yeah, got it. I'll
Mm.
go through this specific case as what exactly will happen in this case, and then we'll be having a discussion in the next session. Because obviously means if the data that is to be processed is not in the cache, and the size is not matching with the cache, so how exactly the switch happens and
I'm just trying to understand the what is the how this performance is maintained, because ultimately the whatever the concepts we are reading, that
yeah, yeah,
LOR is the one which is actually gives us. I mean, these are the certain things which are actually adding the performance, right? These are the
correct,
factors.
correct, correct.
So,
Yeah.
but in case of we have the larger sizes of data,
Mm-hmm.
more than the cache, and
Mm-hmm.
that overall data has to process. In that case, the replacement and all will happen. So, how this performance is maintained in that case? That's what I'm trying to
Yeah, yeah.
understand.
We'll go through it. I'll go through this specific case and then we will have a discussion. because again, I think the infrastructure on which that HANA database will be processed will
Hmm.
not be a generic infrastructure.
Yes, yes,
So I
definitely.
need
It requires a
to,
specific hardware.
yes. So I'll be seeking that what exactly is the infrastructure they usually utilize, and then only we can conclude as what
HANA
exactly
is one use case. But I mean, we can have so many use cases like
anything, yeah, yeah, where we are having data more than
Hmm.
that of the
Yes.
cache space. Yeah, Ajit, you are saying something?
Yeah, one more question on the previous slide. Can you go on that?
Yeah, yeah.
How to decide this catch L1 size, L2 size? How these numbers like this KB, MB, and
Okay, this one. Yeah.
80
Ah,
KB, 2 MB?
so again, this comes with the processing speed and how these L1, L2 caches are being carried out. So mainly, you need to balance two things. One is the speed, and second one is the cost,
Mm-hmm.
right? So what Ravi has asked earlier. So ultimately, we need to maintain a speed so that no way bottleneck should be created, right? Because ultimately, four entities are being there. One is processor. Altogether, five entities are there: processor, three levels of cache, and your main memory, right?
Mm-hmm.
And it all depends what exactly is the processor clock speed and what goes with the size of L1, L2, and L3 cache, so that the required speed or whatever be the speed that the processor is declaring, we can do justice with that particular speed with the required sizes of cache, because L1 and L2 will be residing on your processor cores, and L3
Mm-hmm.
will be something common to it. So that way, just to balance out all these two trade-offs, speed and cost, the manufacturer decides on the size of the L1, L2, and L3 cache. So this way you can see that this is of Xeon system, and you can see that okay, it is 80 KB L1 cache, 2 MB of L2 cache, and 60 MB of L2 cache. We cannot go beyond a certain limit as well, just because okay, it's a Xeon processor. This means that whoever is the end user, he is capable enough of spending a hefty amount, right? So that way we cannot even compare it with the cost, because ultimately the access time, or what we can say the search time. So once you increase the size of the cache, the search time will also increase,
Mm-hmm.
right? So just imagine if something needs to be searched within 2 pages and something needs to be searched within 20 pages. So even if you are having some direct electronics to be utilized, then also the search time will increase a bit, right? So that way, just to balance out these two parameters, one is the speed and the second one is the cost, the manufacturer decides. So if you recall the page, I think we will get it. Just a minute. Right, so you can just have a look. Same i7 processor is there,
Mm-hmm.
and based on different requirements in terms of the hyper-threaded processor or in terms of K processor, F processors, if you see, uh, the cache size is different, right? So this is your L3. So you can see that, okay, it is 4.8, then it is 25 MB cache, 5, then 12 MB cache, but the type is the normal one. that is 14700. Excuse me, here it is hyper-threaded. So that way, just to maintain the balance between the cost and the speed, ultimately you can see over here that as soon as it is being brought to 3.4 gigahertz, uh, there remains no reason that you can come up, because ultimately the customer may be requiring some low cost processor. So that way it is being made 8 MB only, right? So ultimately it's the balancing between the trade-off that manufacturer have to work on, and based on which the decision for the specific size is being taken.
Okay. One more question, sir. Here,
Yeah,
this mapping, whatever the mapping we are direct mapping we are doing, is it from
yeah.
L3 to main memory, or every level of cache has the mapping information?
Yeah, so I'll come to that. It's
Mm.
something that I want you people to brainstorm, but it's good, Ajit, that you came out with this question. Uh, this is for the first time someone has asked me. Otherwise, I keep on going through the content, and finally we had a discussion. But because you have put it into the session, so that we, I request all the candidates, all the scholars, that just have a brainstorm. Don't search it anywhere on the internet. Think out of the logic, because this is a very good question that he has asked, and quite obvious as
I
well.
think I think because the address is being generated by the CPU, so it will be referring to the same address at all level. That's
Yeah,
my understanding.
that's the beauty. At all levels, and not at all levels, but every levels you will be having the mapping. That's the beauty
Yes, yes.
means. Yeah. So I'm having one animation corresponding to this. So once all this is over, then we will go through that animation, right?
Okay.
Yeah. But good that at least you are going through that particular level depth, right? So we'll quickly see. So this is just to make you understand the overall concept. It's not happen this way, but at least you can catch the things quickly. So that's why I have told you that when it is directly mapped, it will be something like this, where corresponding to a block, there will be a specific line within the cache that will be reserved because it is directly mapped, and whenever some address will be there, it will be picking up directly this particular block. So this is what I told you, that I mod 2 to the power k. So if k is the number of bits corresponding to the cache address, right? So here for this, we will be needing 2 to the power 2, ultimately 4, right? So that way, uh, one and same. I told you in terms of line number, or what you can do is you can calculate it with reference to the bits required for this. So for addressing these 4 blocks or lines, I will be needing 2 bits. So ultimately, I mod 2 to the power k will be the basic mathematics. Okay. So this is just to make you understand on a quick way, but because in system everything happens in a binary way, right? So that can be interpreted this way, uh, right? So just a minute. Okay. So in everything happens in binary, so that you can just have a look. So correspondingly, whichever be the number of bits required to address your cache, so those least significant bits will be deciding on the specific line number of the cache, right? That will be mapped, or that uh, will be the block will be transferred. So you can just have a look. And the color is adding up to the whole logic. So 0 1. So ultimately, it will be mapped to the 0 1th block. And because it is direct map, so no complications are there as far as the understanding is being considered. Okay. Now, how can we find data into the cache, or how we can see the tag bits? So we can just have a look. So tag bits are already there because of the difference between the main memory and your cache size. So because of the difference in size, the tag bits are already there. And just have a look. So corresponding to index 0, 0, 0, 1, 1, 0, and 1, 1. So these are the tag bits. And if you replace something, then ultimately tag bits may be different, and that way you can see that whether a cache block is a valid or not. So we will understand it by example. So just try to see this. So 0 0 is the index, tag bit is 0 0. 1 0 corresponding to this is the index of the cache, and tag bit is 0 1. Okay, here it is 1 1 and 0 1. So if because arrow is already being drawn, so this is 0 1. So these tag bits should be 1 1, right? Just see the block. This is the line number. So this is already being there. And if we have to assure that this block is the same, then ultimately the tag bit should be 1 1. We will try to understand it this way, right? So once we have both the tag bits and index bits common, so that way we can tell that which
Hello.
main memory
Uh,
block is there.
Sorry, sir. I had a
Yeah,
network issue.
Ravi.
Can you please go back to that?
Yes, yes.
Yeah, in this one, the looking at the index of the main memory, the least bit 2 bits are looks like their index, and the other 2 bits looks like an tag bit. Is that correct
Correct, correct.
understanding?
Whatever remains apart from the one required for addressing the cache, right, will contribute towards tag.
Okay.
Again, we are dealing with direct mapping, right? Right now, we
Mm.
haven't touched any other mapping technique. This way, we are doing the direct mapping only. Okay. So just to check which specific block is there, or which particular memory main memory block is there in the cache, right? So that way, you can just map it and make a decision as what exactly is the block number. So say it be if I pick anyone with this green, so supposedly 1010 always also corresponds to green. So when I check that whether 1010 is there, so I'll check the index 10, but when I check the tag, so that tag is 01. It is not 10, right? So that way I can make a decision that okay, the block I'm looking into the cache is not present over here, right? So this is the smallest thing we can have. And apart from that, there is one more bit that is being added sometimes in the cache through the processor manufacturer, known as the valid bit. So if the valid bit is set to 0, that is, all the system has recently been initialized and the valid bit is set to 0, right? And 0 in the sense that, okay, data is not valid. And whenever the data is loaded corresponding to any memory and that cache block is being populated, so that way the valid bit is set to 1. So just have a look. If looking at this diagram, you can say that these are the two valid bits. This means the data that is there in these two lines are only a valid data. Rest of the data means even if it is, it may be having some meaning, say it be 1101 or 0110. So again, this may be a valid cases, but again, there may be a case that the data has been replaced or so, and that's why the valid bit is not set, right? So that's why we cannot go with this data, but definitely valid bit is set for these two, and this way we can say that 0000 and 0111. So these two, because tag bit is 01, so I have taken tag bit and followed by the index bit, that is 11. So these two memory block addresses are valid and available within the cache, right? So main memory address in the cache, this is already invalid. Again, this is invalid. This is valid, but it is 0111, and this is all zeros, right? So this is the basic example. You can just have a look, corresponding to the electronics as well. So just see that whatever be the address, uh, you can see that, okay, this is your tag, this is your line, right? And here it is the index based on the valid, based on the tag, and based on the data. If it is a hit, then data is transferred to the CPU. Okay, so I think direct is quite simple. Means your valid bit is checked. Apart from that, address, that is the tag bits and line is being checked that whether it is matching. And because it is direct, means why we are calling it as direct, because corresponding to every block, there is a designated line within the cache, and it is all addressable through uh, the electronics, right? Means appropriate electronics is there. You can see that these AND operation is there. And once the comparison happens with that of the tag and data, so that way you through this AND gate you are having the hit, and once it is there, the data will be transferred to the CPU, right? So what happens on a cache miss? What Ravi and Ajit have asked. So ultimately, if a cache miss happens, the data needs to be brought into the main memory. Sorry, from main memory, it needs to be brought into the cache based on the algorithm. And apparently, uh, we need to add up that particular time as well in the overall operation so that we can have a comparison, right? So if CPU implementation access main memory, their cycle time should have been much larger. So instead, the assumption that is being made with the cache hits, and it will allow us for a shorter life cycle, right? So this is the logic that we have already discussed. Loading a block in the cache, this already we have seen, uh, because the least significant bits corresponding to the number of bits required to address the cache. So here we can see the number of bits required to address the cache is 2 bits, and these two least significant bits will be giving me the line number, right? So that way we can load a block within the cache. Once the data is loaded, the valid bit is set to 1, right? What if cache fills up? Obviously, the third question that we asked. So ultimately, some replacement algorithm is being utilized, and based on that replacement algorithm, we have to make a decision as what exactly is the case. Right now, there are cases where we can have the logic of spatial locality, what Ajit have specified, and the logic of temporal locality. So this is in terms of space. Uh, Ultimately, now we can optimize as which block needs to be brought into the cache, right? So one is in terms of space, another one is in terms of time, the temporal one, right? So if something is being utilized thrice, then we may be needing it further as well. Or in terms of space, say it be if 1001 is being utilized, then there may be a requirement, there may be a subsequent requirement of 1010. So this is in terms of space. I hope you got the point. So this is main memory. If this data is being required by the main memory, sorry, the processor, right? So if it is being required by the processor, then may be the case that this will also be required in future time. May or may not be, but again, it all depends on the concepts of caching, and this is the power of algorithm. The way you are running the algorithm, the way nowadays in caching, ML algorithms are also being utilized that learns from the past behavior, not in the cache, but we will see further the other logics, just like DNS and CDN, where it is being utilized. But this is in terms of space. So how good if we transfer the two blocks when one block is being required? So what will happen is whenever the reference to this next block luckily happens, right? So that will not lead to a cache miss, rather than that it will lead to a cache hit, because we have predicted, we have presumed, because of the spatial locality, that if this block is being required, so there may be a case where a subsequent block may also be required, and when the request for this block was made, we have transferred this is in advance. So in case if the reference is being made to this block, then obviously it will be leading to a cache hit. And how can we reduce the number of potential conflicts? So temporal locality, nearness and time. What does it mean? Data being accessed will probably be accessed again soon, right? So this is known as temporal locality, and based on this, you may have to take the decision if some data is being used now. So what exactly is the probability that the same data will be used in near future? And while in terms of spatial locality, we have discussed that nearness and address, in the sense that if this is being picked or required, so why not we transfer few other blocks as well, so that uh, because of this nearness or because of this spatial locality, if the reference to this block is again made, then it will not lead to a cache miss. Okay, so it's 9:36. We'll have a quick break of 3 minutes and then we'll resume, right? Okay, resuming the session. So performance. So I think you might have calculated it. Ultimately, whenever we will be having a hit or miss, so ultimately the overall performance will be based on these three parameters. One is the hit time, the miss penalty, and the miss rate. So, because again, what exactly is the hit time it is taking, uh, or time it is taking whenever it is a cache hit? Miss penalty, say it be the additional time that will be required in case it is a miss, and what exactly is the rate at which it is being missed, so that mm, simple mathematics is there. So if you have to calculate the average memory access time, so this is what I was talking about when Ravi, you were having the question, that ultimately I just have to assure that this average memory access time is coming lesser than that of uh, if I would have accessed the memory directly. Right. So till the time when we are calculating this average memory access time, and this A, suppose this is X, and if my average memory access time is less than X, right? So till the time it is less than X, then it's a win-win situation by utilizing the cache. At a later stage, say it be if this increases and my average memory time access somewhat increases than that of X because of the cache miss, ultimately it will not be having a good sign, right? And mostly in such cases, your system hangs, right? So that is something we usually don't witness nowadays, and that way we can trust that the algorithms that are being written in order to bring the data, the required data, or the data that needs to be brought into the cache or not. So that way, and the whole calculation is working. Okay, so we can have a quick numerical on this. So if we assume that 33% of the instructions in a program are data access, right? Just a minute, I lost my pointer. Yeah, just a minute. Mm. Okay, sorry for this. So 33% of the instruction in a program are data access. The cache hit ratio is 97%, right? So, and the hit time is 1 cycle, but the miss penalty is 20 cycle. So what exactly will be the average memory access time? Okay, so here the twist that is being given is this, that is 33% of instruction is data access, right? So uh, just have a look, because it is 97%, that is the hit ratio. So that's why the miss rate is merely 0.03%. Okay. So calculating the average memory access time, hit time, obviously hit time will be when considering it as ideal case, and miss rate is 0.03, and the miss penalty is 20 cycle. Excuse me. Hit time, it is being given that it is 1 cycle. So that's why it is written as 1 over here. And once we do this, so the average memory access time for the data that is 1.6 cycles. Now, why it is being given as data? Because rest it will be 1, because here it is cache access. So that's why we are calculating the average memory access data. For rest of the instructions and all, it will be 1. So that way we can calculate the average memory access time overall. So overall it is going to be 1.2 cycles instead of uh, uh, the 1 cycle, right? So that is the overhead it's being there. And we just need to check, or we just need to calculate as how many cycles may be required when we are accessing the memory directly, right? So if it is coming to be less, if this difference is coming to be the less than that when we would have accessed the memory directly, the number of cycles that have passed, because ultimately cycles is in terms of frequency. So or somehow it is related to time again. So if more number of cycles are being required for accessing through the memory, then ultimately the time that will be required is more. Okay, spatial locality, we have already seen that uh, if 1 byte or one some data is being accessed, there are fair chances that the nearby data will also be accessed. Excuse me. So uh, the same electronics or the same calculation we have seen earlier. So this can be done that instead of fetching only one block, right? So we are not fetching only one block, just to take the advantage of spatial locality with an assumption. If this block is being sought by the processor, then there are fair chances that any subsequent block may also be sought in near future, right? And that's why now whenever uh, we will be fetching or we will be replacing any memory address, so that way what we'll be doing is, rather than transferring one block, we will be transferring two blocks. Okay, what will be the difference in the binary arithmetic? Okay, so logic, I think you are able to correlate. So earlier what we were having is 0, it was red, 1, it was blue, 2, it was green, and 3, it was uh, whatever this color is. I don't recognize it correctly. So let it be pink. Okay, because we were picking only one block at a time. But here, whenever a reference is being made, so we will be picking up two blocks so that we can take advantage of the spatial locality, right? So now things will change, and a basic arithmetic that we were doing. So this is in terms of that block address, but nowhere we will be having this numeric calculation. This can only be done when we are doing it from our end, but when it comes to machine, it will be on always a binary arithmetic, right? So appropriate block needs to be picked. So ultimately, to determine the block address of byte address I, again we will be doing the same thing, that is I by 2 to the power n, right? And say it be memory block 12 and 13, both corresponding to block address 6. So ultimately, whenever moved, they will be moved in pair, right? Because both of the modulus is 6. We will see with a numerical, right? So this way things will be there, and we will be able to see the difference in the overall structure as well. Because earlier, if you remember, then we were having tag, and apart from that, uh, what I can say, index, right? Only these two categories were there. But because now we are moving two blocks, or say it be 2 to the power n blocks, so ultimately we have to make a decision as how these bits needs to be taken care. Replacement will be the same. Okay. So now see what exactly will be the difference. So earlier it was only tag and index. Okay. Now there is one more bit. Okay. And that will be your block offset. Okay. Because why this is the case? Because we are having two blocks within one pass, right? So for two blocks, how many bits will be required? So ultimately, we'll be requiring one bit so that whenever I need to refer to a specific block, right? So if I have to refer to the left block, I'll be checking that if this bit is 0, then this means that left block is to be referred. When I need to refer this block, then I need to check that whether the value of that bit is 1 or not. Okay. So from where this bit will be coming? Yes, anyone? The address line is constant, right? So whatever be the address line is there, that is constant, constant, right? So how we will be bringing this block offset bit, or from where we will be taking out this bit? Yes, anyone, Ajit, Ravi, or anyone else? Okay. Uh, just see, earlier, if you recall, then tag bit was 2 bits. Okay. Now you can see that tag bit is only 1 bit, and uh, the remaining 1 bit we have taken for the block offset, right? So it will look like this, that okay, tag will be there, offset will be there, and then my index will be there. Right? And again, the rest of the things will remain same. It will check that whether it is a valid bit or not. Along with that, it will check the tag, that okay, if a tag is valid, because now 1 bit is being used for tag and appropriate index is being referred. Once it has reached to that pair, after reaching to that pair, it refers the block offset, and based on the value of block offset, just like I told you, that for the left we may consider 0, for the right we may consider 1. Because this value is 1, it is considering the right one, and this particular block is passed as data. But now what is the advantage we are having at the later stage? If this particular block, because of the spatial locality, is at all being referred by the processor, right? So that way it will be a cache hit, means that data will be found in the cache only. And just for taking the advantage of a spatial locality, we are going through this practice. right? So this is the case. So what exactly is the disadvantage of direct mapping, right? You might have observed it right from the beginning. Supposedly this is the memory structure, okay, and this is the cache structure. So as of now, only one block of the cache is occupied and three blocks are available, right? Three blocks are available. So one occupied, three blocks are available. And if the memory reference made by the processor goes in the sequence that 0010, 0110. So if this is the memory sequence that is being referred by processor, so you can just have a look. Even when three blocks are available with me, then also I don't have any option other than to replace the 0010 when the request for 0110 is being made, because it's being directly mapped and there are few specific blocks only where I can place the data, and even when other blocks are available, uh, because of the approach I cannot utilize those available blocks. Okay, so this is the main disadvantage of directly mapped. So can we have the other extreme? So this is the one extreme where a specific block is being designated, and in case others are also available, then also we will not be having an option. The other extreme can be, can I have a freedom that among the four blocks, I can put the data anywhere, right? So can we derive the electronics in such a way that we can put the data anywhere? And if this can be done, right? So that is ultimately your fully associative cache, right? So what does it mean? So the data, it will give you a freedom to store the data in any cache block instead of forcing it to a particular block. So what does it mean? But now see the level of complication you have to go through in terms of electronics. Okay. So this you are seeing in terms of three lines, right? So if I'm having 60 MB of cache, okay, and supposedly my data which is there is of say it be 1 KB, okay. So just imagine 60 MB divided by 1 KB, right? Altogether 60, and if I consider it as 1000, so altogether such 60,000 N gates, right? So such 60,000 AND gates needs to be utilized for getting the availability checked, or where exactly the data is being placed. So to check that, ultimately we will be needing the 60,000 gates, right? And then only we will be able to predict the hit. See the difference with that of mm, your direct access. So this is the direct access. Have a look. I don't have to do much because it's a direct access, and I know that if corresponding to this tag, and this line number something is coming, I know that the line number can be directly located and only one gate would have done the whole thing. But apart from that, here I will be needing this much of complicated electronics when it comes to fully associative memory, right? So can there be a midway so that neither I'll be losing the number of blocks as compared to the direct access, but at the same time I don't have to get involved into these common or this complicated electronics, right? So one extreme is direct, other extreme is associative, and the midway is set associative. So what does it mean? So you can just have a look. So this is one-way associative. Uh, One-way associativity is ultimately your full associativity. You can place anywhere. Two-way associativity, in the sense that if altogether 8 blocks are there, then you will be have a set of two blocks, right? So what does it mean? Now, if you do the modulus, right, and now if you want to do the mapping, that zeroth block can come either over here or that fourth block or that eighth block where modulus was coming 0. So that can be brought uh, over here. That can be uh, kept over here in any of the two. So we'll be having a freedom. At the same time, my electronics will not be complicated because now the number of gates are almost halved. Okay. Can be some another option where I am having four-way set associative, where uh, I'll be choosing any of these four locations. So whenever the modulus is 0, so what we'll be doing is we can choose any of these four locations, and definitely the electronics will be more complicated over here as compared to two-way set associative, right? So we'll quickly have a look. Say it be 3. So 3 can be present in any one of these blocks. So that's why it is being made green. It doesn't mean that in all the blocks it will be available. The only intention over here is that if 3 is to be placed, then in two-way associative, I can place either here or here. In four-way, in any of these four blocks, we can place it. And that way we are taking the advantage of both direct uh, and associative. So we are having a midway solution for that. Okay. So we'll quickly. So I think this spectrum is clear to you. Direct mapped is one extreme where it is fast to access because direct electronics is there. You don't have to do the offset and all these calculation. Okay, conflict misses will happen because specific blocks you are designating. While in case of fully associative, you can see that it is somewhat slow to access because the number of comparison will increase drastically. But what happens is here no conflict misses will happen because you will be having ample option to store the block. And this is something the midway or the n way where you can choose the associativity and accordingly you will be having a slower to access or fewer conflict misses. So this is your multi-level cache. We'll see. We'll quickly go to the numericals, looking into the time so that at least you can start brainstorming the things. Okay. So if this is the case, where we are trying to take the advantage of spatial locality as well. Okay, just try to understand how things are going on over here. Okay, so just see that within this, there may be W0, W1, W2, W3, right? So this is 128 words. This is 16 words. Okay, what does it mean? That whenever B0 is to be transferred from memory to cache, so all these four words will also be transferred, right? So that's why right from the beginning I have written the logic that okay, it will be the spatial locality that will be considered. Okay, so B0 or anything, because now here I am having four lines. Okay, so for four lines, I'll be needing 2 bits. Okay, so first thing, what I suggest is you have to calculate the total number of bits so that once I have the total number of bits, so later on we can bifurcate. So the first step is to calculate total number of bits. How will be calculating total number of bits? Yes, anyone?
Number of lines, L0 to L3, 4. So we
But
need
ultimately, we need to set the tags as well, Ajit. So that way, uh, rather than cache, we have to start with memory. That how exactly we can, because again, recall that the processor will be generating the address that will be accessed, means both cache as well as your main memory needs to be accessed. Right? Altogether here we are having 128 words, and here if I talk in terms of blocks, so it is 32 blocks. But we don't have to see in terms of blocks. Ultimately, it's the words that I need to refer. So first of all, total number of bits. Anyone who can tell that what will be the total number of bits that will be requiring to refer each and every word uniquely. Yes, I'll be happy if anyone other than Ravi and Ajit can answer this. And numericals are somewhat very easy to score. Just make it a point. So whenever numericals are there, at least you should put much attention. And I assure you that it will be time saving rather than when you will be studying. And instead, if you go through the session, so the time within the session will be somewhat less than that of the time you will be taking to understand the core concept, because even the numericals will not be direct. So for building the concept, better if you go through the session. Yes, Ajit, if you can tell me what will be the total number of bits.
what I can think of this 2 to the power 5 plus 2. 5 plus 2.
Very good. So you have done bottom up approach. I was trying to go top down. Very good. So it's what he has done is he has thought in terms of tags as well as the lines, or what we can say the blocks. So that way he has calculated. But directly, if you would like to calculate, so ultimately you have to address 128 words, right? So 128 words, if you would like to address, then ultimately it is 2 to the power 7 that goes to 128. and therefore total number of bits will go to 7. And that's why I was saying that my approach was top down and Ajit has done bottom up approach. So now it's for sure that the address will be of 7 bits. Now corresponding to each and every methodology, say it be direct access, right? So within direct access, now I have to classify that what exactly will be the fields. So in direct access, uh, tag will be there. Then apart from that, line will be there, or specifically bits corresponding to line number will be there. And finally, the offset will be there, right? So direct access means obviously means if we have to refer to the memory, definitely this 2 to the power 7, 7 bits will be required. But what in terms of cache, right? 4 lines are there within the cache. So how many bits I need to I will be requiring in case I'll be needing to refer 4 lines. Obviously 2. So line number is sorted, or we can go other way around as well. Because there are 4 words within a block. So to refer 4 words, again I'll be needing 2 bits. So I am done with the offset. Now line number, because there are 4 lines again. So I'll be needing 2 bits for the line number, and whatever remains, just put it in tag bits, right? So in case of direct, you will be having tag as 3 bits, line number 2 bits, and offset 2 bits. So what does it mean? We will have an example. This is just for having an example, right? Means altogether you never have some 7 bits case. Okay. So suppose there is an address, say it be 001, all right, 001, then 1011, right? So what does it mean? So this is tag bit that will be checking for having the exact data, or just check that whether the memory data we are looking for is there in the cache or not. So we don't have to do much in this. Now tell me that in which line number and in which offset this particular reference to the address will be made. Although only Ajit and Ravi are replying, so I'll go with this. Right, so if this is the address, you can see that these two corresponds to the line number. So 10 is, this is 00, this is 01, this is 10. So this means that the data that is being there should be in L2, and offset is 11. Means whatever be the word, say it be, if it corresponds to W1, W2, W3 in W4, sorry, W0, 1, 2, 3 in sequence. So because this is 1, 1, so ultimately the request is referring to this particular word. So this way you can have the interpretation. Okay. What about fully associative? You should be clear about the categories that you will be requiring. Okay, fully associative, because you can put the data in any line number, right? So that way it will be only tag and offset. I hope you got the point. Here in direct access, there was a specific line number where only the data can be placed. And that's why we need to consider the line number. While in case of fully associative, I just have to check that, okay, offset, because that's very much required to pick a specific word. So 2 bits will be required for offset because 4 words are there. And whatever remaining, because it is fully associative, you can put rest of the bits into tag. Okay. So this is the case. So what will happen? How this address will be interpreted? Again, take the example. So ultimately, what the electronics will be doing is it will be identifying that where exactly this tag corresponds to 00110, and based on that particular tag, so it will not be specifically to the line number L2. It may be present in L0, it may be present in L1, it may be present in L3 because of the property of the map, excuse me, because of the property of the mapping that is fully associative, right? And based on the tag that is being associated with the address, and based on the tag corresponding to the tag available within the data of the cache memory, the electronics will be finding out that, okay, this specific case is being stored in L0. So accordingly, whatever be the, excuse me, whatever be the third word corresponding to L0, it will be fetched. So this corresponds to fully associative. Now, what will happen with respect to two-way set associative, right? Now, you just have to tell me the categories. So obviously, offset will always be there because we are dealing with the concept of spatial locality where we are utilizing 4 words. Offset 2 bits obviously means in no case it will vary. Okay. Next will be the set number because we are utilizing two-way set associative. If you go to the diagram of two-way set associative, then this is the case. This is your two-way set associative. To identify a specific set, right? So earlier we were dealing with offset that, okay, within a block, what will be the value? But now within two-way in the sense, you can just have a look at associative. So these four are random, means we can place in any one of the set. That is, if either I can place it over here or I can place it over here. So earlier we were dealing with the horizontal uh, offset, but now we have to identify the vertical offset as well. So if it is two-way set associative where two possibilities will be there, right? So for identifying uh, the offset within the set, right? How many bits we will be requiring? Ultimately, it will be one bit that I'll be requiring. I'll make it clear from here. Since this is example of four lines, so that may create a confusion, but in subsequent numericals, it will be clear to you. So this will be a set, but just make it clear that we just have to bother about the options that I don't have to bother that how many total sets will be there because it is two-way set associative. I just have to find out whether the data is there in the line L0 or whether the data is there in line L1, right? And because rest will always be taken care by the electronics or the circuitry to be very precise. So rest will be taken care by circuits just like the associative memory. But at least I need to make the differentiation that among the two blocks within a set, as two-way set associative is there, I will be needing one bit. Whatever remains, I'll be putting it into tag bit. That is 4. So this is direct, this is fully associative, and this is two-way set associative, right? So this way, you will be having the whole calculation in terms of the mapping, right? So that's all for today. Any questions? Okay.
Sir Ravi,
Yeah,
I
Ravi.
I was referring to the handout for these two chapter. I believe this is second chapter we are on
Yeah,
memory
yeah, we are
optimization.
on second. Yeah, yeah.
So for chapter one, I was the textbook reference was given. I mean, it is not completely there, but any suggestion apart from the textbook? What are the other things we can refer? Because and come on, just
Okay,
to
so
continuation actually, because the slides and all what we have topic wise, if I'm trying to find out, it's not completely that we are able to
single
find.
book, yeah.
Yes,
Uh,
yes.
the syllabus itself is framed in such a way that not even single, but even if you carry 3 to 4 books, then also it will not cover the whole thing.
Yeah,
So
yeah.
try to means what I'll do, I'll still try to streamline as which topic you can pick from which particular book. So just give me some time. I'll map that and we'll share it in Microsoft Teams.
Okay, sir.
Sir,
Thank you.
some
Okay.
books, if you have the PDF, can you upload in Teams and we can refer?
Yeah, rather than uploading in Teams, I'll putting it into Drive and we'll be sharing the Drive link, right? So you can
Okay, sir.
download it
Yeah,
and later on
yeah,
I'll remove it. Yeah.
fine.
So
Yeah,
that
that
I'll
will
do.
help us. Yeah.
Yeah. I'm having all the PDFs, so we'll be sharing it. Okay. Okay. Anything else? Okay. If nothing is there, then thank you. Uh, it was a wonderful session and a special thanks to Ajit and Ravi because of having the interaction. We keep on motivated, right? Thank you. I'm ending up the call.
Thank you,
Thank
sir.
you.
Thank you.